So we got a taste of density in the worksheet that you did in the activity session. Now I'm going to formally teach you. I was hoping to get to this last week, but it didn't happen. So density. Density expresses the concentration of mass. It's the mass of an object divided by the volume of an object. So you can kind of think of it as the heaviness of an object. My children tend to be very dense. And you pick up if I had a 2-year-old, and he's probably going to weigh 30 pounds. But he doesn't look that big. And you pick him up and you're like, whoa. And then you pick up the neighbor girl across the street and she seems light as a feather. They're the same height. They look like they're the same size. But one of them's really heavy and the other one feels really light. That's density, okay? You've heard that joke, which weighs more, a pound of feathers or a pound of bricks? What's the answer? The same. They're both a pound. But which one takes up more space? Pound of bricks or a pound of feathers? Pound of feathers is a lot of volume, right? To have a pound of feathers. And a pound of bricks is probably not even a whole brick. That's a difference in density. Density is an intrinsic property of a substance, and it doesn't change when you cut the object in half or if you have more or less of it. The density is going to be the same. So density is a concept that we use a lot in chemistry. Because of how the original metric standards were defined, they were based on water. They defined a kilogram as equal to the mass of 1 liter of water. And that gives us this lovely relationship that the density of water is 1 gram per milliliter. Now, it does vary slightly with temperature, but in terms of just a rough estimate, the density of water is 1 gram per milliliter, so that can be very convenient. We can express density in different units. Grams per milliliter is frequently used for volume because the volume, did I say volume? Good grief. For liquids, because the volume is measured in milliliters. Grams per cubic centimeter is the common unit for solids because you think of a rectangular solid, you're measuring the sides in centimeters and cubing it. And gases are much less dense than liquids and solids, and so we tend to use grams per liter. And here's just a comparison of some substances. Here's ice. These are 1 cubic centimeter sections of these different compounds or elements. Ice is going to weigh 0.91 grams. Water would weigh 1. Ice is a little bit less dense than water, and that's why ice floats. A 1 cubic centimeter piece of lead would weigh 11.3 grams. And if you had osmium, which is an unusual element, 22.5 grams. Very, very dense. You see these equal volume cubes, and the osmium weighs 22 times that of the ice or the water. It's much denser. We can estimate density in comparison to another object or liquid. So here's a graduated cylinder. I do a demo like this in one of my classes. We have 3 liquids in here. This one in the middle is water. Water will float on a liquid that is more dense. And up here we have a liquid that is less dense than water, and that floats on top of the water. This object, S1, must be less dense than the water because it floats. Something that is more dense will sink. So S2 is more dense than the water, but it's less dense than this liquid at the bottom. And this object here at the bottom is the very most dense. And so we can compare their relative densities. We can say that liquid 1 is less dense than solid 1, which is less dense than water, which is less dense than solid 2, and liquid 2, and then solid 3. And so that's a way to estimate. Here's some densities of selected objects. Sometimes you need a density to do a homework problem, and they don't actually give it to you. And so then that's something that you just go look up. We don't expect you to memorize densities except for the density of water, which is 1. And so you can see the densities vary widely. Solids going from about 0.9 up to 19 in this table. But gases, these units are grams per liter. Hydrogen has a density of 0.09 grams per liter. That's very different than water. So we can calculate density. Here we're asked, what is the density of a platinum nugget that has a mass of 224.50 grams and a volume of 10.0 cubic centimeters? And for a problem like this, you need to remember what that density equation is. So density is the mass over the volume. And here, this is a nice getting started problem. They're giving us the mass. So this is mass. They're actually telling us it's the mass, but if they didn't tell us, we should be able to look at the unit and we should know that gram is a unit of mass. So we're going to put 224.50 grams in the numerator. And then this is the volume of 10.0. Now we want to use our knowledge of significant figures, so we're going to write that whole thing down, 10.0, and write the units in there. And then we get out our calculator. Well, we really shouldn't need a calculator for that one, should we? We're just dividing by 10. So that's going to be 22.45. That's what your calculator is going to show you. And what are the units? Do they cancel out? No, they don't. If units don't cancel out, you just carry them over. And so that's grams per cubic centimeter. Now, how many significant figures should that answer have? It should have 3, because this number in the bottom has 3. So I wrote down what my calculator says, and then I'm going to rewrite it with the correct number of significant figures. I need to round that 4 up to a 5. And there's my answer. Any questions? The density equation, density equals mass over volume, is something you need to memorize. Now we can also use density as a unit factor, and you probably encountered this in your worksheet. Density gives us a relationship between mass and volume that is specific for that particular compound. So here's an example. An automobile battery contains 1,275 milliliters of acid. If the density is 1.85 grams per milliliter, how many grams of acid are in an automobile battery? Now this problem can be solved using algebra and the density equation. And if you want to do it that way, that's fine. But I really recommend that you try the unit analysis method. I think it ends up being simpler once you get used to the idea of it. So we're going to look through this problem, and I'm going to write down the numbers, because that's a good approach to solving word problems. So 1275 milliliters and 1.84. This is written as a horizontal fraction, which is easier to type. But you're not typing when you're doing your work, so write it as a vertical fraction. And then you can see that that's actually a unit factor right there. 1.84 grams per milliliter, and that would be 1 milliliter in the bottom. So we wrote down our numbers. Then the process tells us to ask ourselves, what are we trying to find? What unit are we looking for? We're looking for grams, right? So we're trying to find grams. And what do we start with? Sometimes that's hard to figure out. If there's only one number, it's easier. But here we were given 2 numbers. Do we start with this one or this one? Well, look at the units. This one could be used as a unit factor. This one cannot. And sometimes they throw in extra numbers, which is really kind of mean, isn't it? But because this is a single unit, this is going to be the one we should start with. And so we're going to go from milliliters to grams. This is the unit factor we need for that conversion, and they gave it to us in the problem. Sometimes you may need to go look it up in a table in your textbook. So now we put in our 1275 milliliters and our unit factor, and our path is very simple here, milliliters to grams. So we're going to go milliliters to grams in the numerator. And then I'm going to take this unit and pull it down so it cancels out. We'll put milliliters down here. Because we're analyzing the units. They're telling us what to do. There's no figuring out, do I need to multiply or divide? We're just looking at the units. And now we go to our unit factor, which is the density, and we see that 1.84, it's very far to the 4, 1.84 is with grams, and so it needs to stay there, 1.84. And there we have it. So we take 1.84, no, my goodness. I stayed up way too late last night, and I got up way too early. And this is what you get. This is me on Rockstar. 1275 times 1.84. Calculator says 2346. And the only unit left there is grams. So we write down what the calculator says and the unit, and then we ask ourselves how many sig figs? 3. Our starting number had 4, but the density only has 3. Density is not an exact conversion factor, and so it can limit our sig figs. So if we need to round this to 3 significant figures, we're going to keep that third digit there. This is the tens place. We have to be really careful when we round off anything above the ones place, because we do not want to round this to 235. This is 2,000 something, right? So a safe way around that is to first put it into scientific notation. So 2.346 times 10 to the third, because the decimal point was here, and I'll move it 3 places. Now if I round off, I don't have to worry about putting in placeholder zeros. And so I'm going to give my answers 2.35 times 10 to the third grams. As far as I'm concerned, it is never incorrect to give your answer in scientific notation. For my worksheets and stuff, if it says report the answer in scientific notation, then you have to. If it doesn't specify, I will accept either. But I think scientific notation is usually better. Any questions? That's using density as a conversion factor. Yes?
If you were to just leave it 234 and just put a 0, or 235 and then put a 0 where the 6 is, would that be okay?
That would be okay.
Okay.
2350, that's acceptable.
Okay.
Yeah. I think in the box is the best answer, but using a placeholder 0 is acceptable. Any other questions? Yes?
Instead of doing it this way, can you just plug the numbers into the formula you use?
You can plug the numbers into the formula, yes. My experience has been, though, that a lot of people are rusty on their algebra, and when they rearrange the equation, they make silly mistakes, and they get the wrong answer. If you're good with rearranging equations, that might be easier for you. But I think this method just falls into this pattern that we've learned of unit analysis. So for most students, this is what I recommend. But you definitely can use algebra in the equation, yes. Any other questions? Let's just do one of these. We already did a mass one, so let's do this top one. So the density of mercury is 13.534 grams per cubic centimeter. How many cubic meters are in 5.92 times 10 to the 4th grams of mercury? Because I'm not going to do this problem at the bottom, I'm going to get rid of it so I have more space. And I don't know why that's fun for me, but it just is. I don't know, it's like coloring or something. Okay, so let's take these numbers and just write them down so we can see what we're dealing with. 534 grams per cubic centimeter. Write that as a vertical fraction and then extend that line. And I've got 5.92 times 10 to the 4th grams. What am I looking for? Cubic meters. So over here, I'm going to write cubic meters. Which of these numbers am I going to be starting with? The bottom one, because this is just a single unit. This is a density. I'm going to end up using that as a conversion factor. So I'm going to start with grams. Can I go directly from grams to meters cubed? Does this give me a relationship between grams and cubic meters?
Yes.
That looks like cubic centimeters, right? This gives me grams to cubic centimeters. So I could do grams to cubic centimeters, and then I can go to cubic meters. Some students like to combine lots of things together, and that can be dangerous. It's like taking a shortcut but getting lost. So I don't necessarily recommend cramming things together. It's better to take a couple extra steps and get there successfully. So now we just write it all out. 5.92 times 10 to the 4th grams. There are 2 arrows, so I'm going to have 2 unit factors here. And I look at my path, grams to cubic centimeters to cubic meters, and I write those in the numerator, grams to cubic centimeters to cubic meters. And then I take this unit, and that goes in the bottom, because I want those to cancel out. And then I put cubic centimeters in the bottom. This is the pattern of unit analysis, and it works for all kinds of things. It's awesome. I get all my units in there. Then I go looking for numbers. Grams and cubic centimeters. That's this guy right here. 13.534 is with gram, and so I need to put it with gram. So it ends up on the bottom this time. 13.534. And then some people are bothered if there's not a number there. Chemists, you'll find, have a thing against the number 1. We don't write it unless we absolutely have to. But for your sake, I'll write a number 1 for you. Okay, so because 1 cubic centimeter is equal to this. Now, this guy, what did we learn about doing cubed units? First, we look at without the cube. So I'm going to take these guys off for a minute. Oh, look, there's something underneath. Go away. What's the relationship between meters and centimeters? Centi means what? 10 to the minus 2. So centi is on the bottom. I'm going to put what it means on the other side. That's the pattern. Now, to get the cubed back, I'm going to cube the whole thing. When I do the math on my calculator, I have to cube the number. Okay? So as I'm going through my calculator, I'll tell you what buttons I'm pushing. 5.92 EE4 divided by 13.534 times 1 EE, change sign 2, and then my calculator has a y to the x button. Your calculator might have a y cubed button. So I'm going to press y to the x and the number 3 to cube it and press equals. And then my calculator is showing me 0.004374169. And the unit there will be meters cubed. There are other ways to approach getting this into your calculator. Remember, when we have that 10 to the minus 2, that's the same as 1 times 10 to the minus 2. Some of you are good with exponents, and you can do this in your head and say, well, that's 1 times 10 to the minus 6, right? Because we're multiplying these exponents. Or you might, another thing you can do is you can put 1 times 10 to the minus 2. You can multiply by that 3 times. That works as well. You need to find a method that makes sense to you and then use it consistently. Anybody having trouble getting that number to show up in their calculator? Everybody okay with that? How should I report this answer? How many sig figs should it have? I hear 3 and 5. Well, this number has 3, and this one has 5, but we're always going with the smallest. So only 3. This is exact, and so we don't even have to think about him. Remember that leading zeros do not count, and so we're going to go to the 7. 0.00437 cubic meters, or in scientific notation, that would be 4.37 times 10 to the minus third cubic meters. Either of those would be very nice. Any questions? You could also do this one with algebra, but you're going to have to do algebra to find the volume in cubic centimeters, and then you're going to have to convert to cubic meters. And I personally think it's easier to just do all of it as one unit analysis problem. I'm going to pick and choose here. Let's do the gallon per minute one. Let's do this one at the top. I wish I could do all of them. I like doing these problems, but there's just not enough time. A gasoline pump dispenses fuel at the rate of 0.20 gallons per minute. How long will it take to obtain 9.50 liters of gas? And then they offer us this little conversion over here. Well, let's just follow our pattern of writing down numbers. Gallons per minute and 9.50 liters of gas. What is the question asking?
How long will it take?
How long? So that's time. It doesn't specify minutes, hours, seconds, days, years. So then we can choose which unit we give. What unit would be easy in this problem? Minutes, because this already has minutes in it. So we're going to say we'll find the time in minutes. And which of these numbers should we start with? We should start with the 9.50 liters because that looks like a unit factor. This is not a density problem, but it is using a density-like expression that's given to you as a conversion factor. So that's probably going to be a conversion factor. So we're going to go from liters somehow to minutes. Well, we search around, and this is where you just kind of have to play with it and investigate. Here I've got a relationship between liters and gallons. So that tells me I could go from liters to gallons. And then this relationship relates gallons and minutes. So I can use that to get from gallons to minutes. This is pulling things together. Creating the path, I really think, is the most challenging part. Just coming up with how am I going to do this? Once you get the path, it's just following a pattern. And I know a lot of you are really good at following a pattern. Okay, so now we follow the pattern, 9.50 liters, 2 conversion factors, because there's 2 arrows. So liters to gallons to minutes, liters to gallons to minutes. Then I take the unit from the previous term and I put it in the denominator because I want those to cancel out. And then I put gallons down here so that they cancel out. The units tell me what to do. Now I look for numbers to relate these two things. Gallons and liters. That's not this guy, but here, gallons and liters. So 1 gallon, 3.785 liters. 1 gallon, 3.785 liters. And then minutes and gallons would be this guy. 0.2 gallons, so 0.2 goes in the denominator. And you can put a 1 up there if it makes you feel better. When you write your work out like this, and this is a very important skill to be successful in 1A, is learning how to write it out like this. You don't have to write this other stuff down if you're good at it, but you should always write this down. Because then you can go back and look at it, check your work if you're doing an exam. If it's homework and you're getting the answer wrong, you can go back and find your mistake instead of starting over. 9.5 divided by 3.785 divided by 0.2. And as usual, the calculator gives me this long, messy answer. And what unit is left there? Minutes. How many significant figures should my answer have? We have to look at what we're doing here. This one has 3, and this one has how many? 4. That's not exact because this is metric in gallons, English. How many does this one have? 2. That's the smallest one. The smallest number of sig figs because we're doing multiplication and division. So we're going to have 2 sig figs, and so we can round this to 13 minutes. Any questions?